So when we left off, we had this relationship that the probability that the random variable y bar minus 1.96 times sigma divided by the square root of n being less than population mean being less than random y bar plus 1.96 times sigma by the square root of n was equal to 0.95. And this guy here, we can think of as random variables. We can think of this as the upper limit and the lower limit. And we can think of the idea we're going to construct a 95% confidence interval as y bar plus or minus 1.96 times sigma, the square root of n. If we consider all possible values of that, then 95% of those would straddle the true mean. Okay, so now we're moving on to the next section, which have been titled the practice. This is the practice. And let's say we go to our high school and we're thinking about IQ, and we take a sample size of 25 and we calculate y bar equal to 110, and then we use this formula to calculate y bar plus or minus 1.96 times sigma, which we know, because we know the population standard deviation is 15 divided by the square root of 25. And what that gives us is an interval that goes from 104 to 116. So that is our 95% confidence interval. And so what I want to talk about is, what the heck does this thing mean? And the way I want to approach that is begin by talking about what it doesn't mean. It does not mean there's a 95% probability that the true population mean lies between 104 and 116. It definitely does not mean that. Now, why doesn't it mean that? Well, let's refresh our memories about what a 95% confidence interval is. Here's a number line, and there's the value right there, the mu, the true average IQ of all the students in that high school. So that is a fixed value. What we do is we go out and we calculate a particular sample, and we calculate an interval. Lowercase l, lower limit, lowercase u, upper limit. And we could do that many, many times. And if we did that an infinite number of times, then 95% of these intervals that we constructed would straddle the true mean. But the point is, we can't speak about the probability of mu being something. This is a fixed item. There's no variability associated with mu. We don't know what it is, but it is a constant fixed value. What varies are the possible intervals that we could get if we went through the process that we went through in the last section. So we know 95% confidence interval doesn't mean that. Here's something else it doesn't mean, and this is a lot more subtle. That there's a 95% probability that the interval (104 to 116) straddles the true mean. That's not true. And the reason it's not true is if we go back to our drawing, there's our population mean on our number line for IQ, and we go out and we get a particular interval. Well, that is a particular fixed value once we've done the experiment and calculated the interval. Now, what we do know is that if we were to repeat this process an infinite number of times and calculate an infinite number of intervals, then 95% of all possible intervals would straddle the true mean. But the particular one that we arrived at, we don't know whether it straddled the true mean. Because once we've calculated it too is fixed once it's been calculated, and either it straddles the true mean or it doesn't. Probability is not relevant. Now, this concept here is a little bit awkward, and you may not actually believe it at first blush. So one thing I've done in the past to demonstrate this idea is to take a coin, pull it out of my pocket, and say, how many of you all believe that the probability if I flip this coin, the probability of it coming up heads would be 0.5? Most people would agree with that because it is a fair coin. And so then what I do is I take this coin, I flip it up in the air, falls to the ground, lies there on the ground. I can see what's happened, but no one in the class can. So I say to the class, here's the deal I'm going to make. I think that coin is showing heads. I'm saying it's showing heads. And here's the bet that I'm willing to offer. If I'm right, and it really is heads, then you have to give me $1. If I'm wrong, and it isn't heads, then I have to give you $10,000. Who wants to take the bet? And no one, of course, wants to take the bet, because everybody in the room knows that if I'm willing to make a bet like that, it's bloody well heads. So at this point, everyone realizes that there's no longer a 50% probability of the coin being head or a tail. So then the question arrives, okay, initially, when I pulled the coin out of my pocket, everyone agreed there was a probability of 0.5 that when the experiment was conducted, it would turn out to be a head. But now, people don't feel that way. So at what point did the probability go from 0.5 to being, well, probability isn't really relevant? And the argument that I would make is that that concept of probability being 0.5 went away as soon as the coin settled down on the floor and showed, in fact, that it was a head. And so that's very much analogous to what's going on here, and that's why we can't say that once we have our particular constructed 95% confidence interval, that there's a 95% probability that it straddles the true mean. So, what good is it? I mean, if we can't say that, what can we say? Well, what we can say is that either one of two things has happened. Either one of two things has happened. Either 104 to 116 straddles the true mean, or 2, 104 to 116 doesn't straddle the true mean. Just like our coin lying on the floor. It's now one of those two things. Now, if this occurs, this would be a rare event. Because remember, with a 95% probability, a 95% confidence interval, then 95% of these intervals straddle the true mean. Our particular interval either does or it doesn't. But if it fails to straddle the true mean, that means that a rare event has occurred. And so, since we tend not to believe in rare events, what we're going to do is we're going to permit ourselves to assume that that interval actually does straddle the true mean. Now, an analogy for this might be a jury trial. So if you consider what happens in a jury trial. What happens in a jury trial is that there's two phases. There's one phase, the determination of guilt, and the other is the sentencing phase. And we as a society have gone to a process that we say, okay, we might make a mistake, but what we're going to say is we're going to determine somebody's guilty if we're sure, and the criteria we use, we've agreed on as a society, is beyond a reasonable doubt. So the jury looks at the defendant, and if they're sure beyond a reasonable doubt that the defendant is guilty, then they render a verdict of guilty. And that's the phase of determining guilt. The sentencing phase. At the sentencing phase, there is no longer any question in the mind of the sentencing judge of innocence or guilt. Guilt has been determined. The defendant has been determined guilty, and therefore sentencing is based on the assumption of guilt, which is all based on the underlying proposition that we've gone through a process such that the possibility that we've made a mistake is actually very low, and therefore the judge doesn't say, well, maybe guilty, maybe not. No, the judge says guilty, and the sentence is based on the assumption of guilt. So now when we think about statistics and research, the standard that we often use is not beyond a reasonable doubt, but rather alpha is equal to 0.05. And that gives us a 95% confidence interval. And a 95% confidence interval goes from 104 to 116. And so in terms of your research, in terms of your thesis, there's the statistical part, sort of analogous to the determination of guilt, and then the next part is the storytelling part, where you try to make sense of all your results. And when you enter the storytelling part, having gone through this process of determining a 95% confidence interval, a process that we're pretty darn sure most of the time is going to give us an interval that actually does straddle the true mean, then you get to tell your story assuming that 104 to 116 actually does straddle the true mean. Okay, now what I want to do is move on to section 2.3, I believe. It will be the next section. And we want to think about alternate forms. Of the 95% confidence interval. And what we've done so far is we say, okay, when we're going to calculate this, we're going to calculate it as y bar plus or minus 1.96 times sigma, which is we assume we know, and square root of n, our sample size. And another way to represent that is y bar plus or minus 1.96 times the standard error. So what's that all about? Well, this is just a review. Remember, what we're assuming is that the underlying population is normally distributed with some mean and some sigma. Right? And that's normally distributed with mean mu and standard deviation sigma. If we considered all possible values of y bar, sum of all the yi over n, what we would get is a random variable. Now we get our random variable capital Y bar, which is normally distributed with mean mu and standard deviation sigma over root n. If we think about our underlying population, its standard deviation was equal to 15. If we think about our current population, its standard deviation is going to be 15 divided by square root of n. So if we assume if we took a sample size of 25, is going to be equal to 3. So where we are is to remind ourselves that both this and this are probability density functions, but this is the probability density function of a sample statistic, y bar. As a consequence, this probability density function gets a special name, which is sampling distribution. And its standard deviation gets a special name, which is standard error. So that's why we sometimes see it represented like that. Now, what we've gone through is a calculation of a 95% confidence interval. We can calculate other types of confidence interval, although they are less common. For example, if we wanted to, we could calculate a 90% confidence interval. So, how would we calculate a 90% confidence interval? Well, what's going to happen is if we got a 90% confidence interval, then alpha is going to be equal to 0.10, and 1 minus alpha over 2 is going to be equal to 0.950. So now we can go to our Z table and find the corresponding value of Z. So let's do that. So the whole concept of a 95% confidence interval is if we come back here, we want some value here and here. So we got 0.05 here, 0.05 here, and 0.9 here. So what sort of value of Z would be associated with a 0.05 in this area here? Well, that would be the value of Z that would give us 0.95 in everything to the left of this line. So we come down here and we look for 0.95, and we see that 0.95 would be somewhere between here, somewhere in this range. So somewhere between 1.6, 1.64, 1.65. So I'm just going to call it 1.645. So let's go back to the whiteboard. So this is a figure from your notes. Earlier we looked at this. Now what I want to look at is this. And so remember, the idea is that y bar minus mu over sigma over root n has a standard normal distribution. And that's what allowed us to use our Z table. So what does this mean? This means if we consider every possible value of lowercase y bar minus mu over sigma root n, that this would be the appropriate probability density function. So we saw from the Z table that if we would have a Z value of 1.645 here and a value of 1 minus 1.645 there, that 90% of the values lie within here. So we can say that 90% of the y bar minus mu over sigma divided by root n are going to lie in this range. So what that allows us to say, knowing that we've got this 1.645 and this minus 1.645, we can now say, if we look at the probability that y bar minus now 1.645 times sigma divided by the square root of n, being less than mu, being less than y bar, now it's plus 1.645 times sigma divided by the root n, is going to be equal to not 0.95, but rather 0.90. So that's the way we can calculate a 90% confidence interval. And so if we go back to the whiteboard, and we see that from our Z table that if 1 minus alpha over 2 is 0.95, then Z is equal to 1.645. So now what we can say is that, okay, if you want a 95% confidence interval, it's y bar plus or minus 1.96 sigma over root n. If you want a 90%, it's y bar plus or minus 1.645 sigma over the square root of n. And all I'm saying is that you can expand this to say that 1 minus alpha, if you want a confidence interval of, let's say, 1 minus alpha. So in the case where alpha is 0.05, you'd have a 95. Where alpha is 0.1, you'd have a 90. Then the formula is y bar plus or minus the z that's associated with alpha over 2 times sigma over the square root of n. So we'll stop there.